start. Is this doing anything? Yeah, okay. So that's on. I'll video provide original background effects, light. Okay, that part should be good. Kind of feeling. Okay, I'm almost done. Yeah, second. All right. Okay. Right. Yeah, you were asking me about what? Both of your question has to do with the.
Is there any like format we have to follow? Any rough format?
So for the final report, it would make sense for you to do it like a regular paper, right? Where you have an abstract, what problem you're solving, you introduce the problem, talk about what existing solutions are, if there are any. Since I'm asking you to do a composite of a bunch of steps, then the odds of that being the case are lower. Then you would talk about each problem that you're solving within it, what the best solutions for those are, and how you're composing the whole thing. Then you talk about your data, talk about methods. If you tried multiple variations, then that would be an ablation study where you're taking out parts or adding parts in and comparing how that changes things. For an intermediate report, I don't expect you to have all of those components, so it wouldn't necessarily make sense for you to structure it like that, since you wouldn't have a conclusion that you can draw, uh, seeing as you're not done building the whole thing. Loosely, if you can follow that sort of a structure, that's good. The downside of doing it that way is that if you submit something now in that format, then the final report, you'll be tempted to just sort of add things to it without changing anything existing. And then that wouldn't make for a very good record of whatever you've done. Because ideally, you should be writing up everything once you know the entire pipeline and the big picture and also the details within it. So, oh shit. Keeping that in mind, just the objective is to document it in a way that has academic rigor, and it should be a step in the direction of something publishable at the end. Even if that's not ultimately what you plan on doing with it, it should at least look like that's what you're trying to do.
Like a small introduction and then set of tasks what we have planned like, in the previous report. We wrote up the tasks that we are planning to work on.
Right. Yeah. So that if you make a table that has a few points of what you were planning to cover and how much of that you completed, that's the easiest way to tell how much progress you're making at a glance just by looking at it.
For whatever we have completed, brief explanation of what we have done and the outputs of till that stage.
Right. Yeah, you're welcome. Ooh, didn't work. Oh. Okay, all of that worked out pretty nicely. I made some changes to my setup from last time, so I'm running this on Ubuntu now because this is something that I always suspected partly, but I never knew for a fact. I was trying to train something on a workstation at my lab that's running Windows because I don't know, it just always has been running Windows, and I was trying to train a model through WSL. And that thing has two 3090s in it. And the desktop on which I do all my prototyping has a 2080 Ti. So it's an older card with less VRAM, but still my prototyping desktop was able to train the exact same model on the exact same data, exact same batch size, all of that about like 3 to 4 times faster per epoch. Um, and I figured that would help with doing stuff here too, because if I'm doing stuff live and I try to train something for 100 epochs, then it'll take forever if I did it in Windows the way I was doing last time. So just had to. Ooh, also, I didn't have the foresight to do a screen recording last class, so that recording that I uploaded is probably not of much use, but I am doing a screen recording now, which is what I was testing a few minutes ago. Um, I'll just do a really quick recap of everything we did last class, just for posterity. I cleaned this up a little bit, added like markdown descriptions of what we did. And I'll talk through this really quick, and then there's something else I've planned to do for today, so I'll dive right into that in a second, because that also might take me a while to uh, finish. So last class, we picked a data set from Kaggle based on what you guys all picked. And it had a bunch of images of brain scans, and the objective was to classify that as um, tumor containing or tumor free, basically. So this is something that I hadn't done earlier, but I added this in. This is basically whatever components have a randomness aspect to it, like initializing weights or picking samples from the data loader. If you set a seed and do that for every component that has some sort of randomness in it, then that lets you sort of guarantee that every time you run the code, stuff should be the same. You should get the same output every time you do things, which is good for demonstrating things and for reproducibility if you're sharing code as part of a paper or whatever. So we explore just the data set since we can make no assumptions about how it's structured. We found out that some of it was redundant. These two folders and these two folders had the exact same content, which we verified manually using some pattern matching stuff. Uh, then just looked at file name formats because that's how we're inferring what class something is. As assembled a mapping of class labels because we can't have yes and no as our labels since the model wouldn't understand strings. So we convert them to numbers. Visualized a few of them and used the Torch Vision image folder class to create a data set. Which was convenient because of the way the dataset was structured with class labels within the top level directory, and then within each class label directory, there's samples for that class. We also went over how to do the exact same thing, but DIY, because you tend to have to do it yourself a lot of the time when that structure is not something that you have the luxury of. And the information we get out of both of those are equivalent. And how I had started out last class, and this part I think was a bit less clear. There were two things we did, which is defining a custom model, where you describe each of the layers and what you want, and the other option is to load something pre-trained because odds are those are already time tested, and there's probably good reason why they're part of the main Torch Vision package. So what we're doing here is we load one of those models, including its weights, and the final layer is a fully connected classifier layer, which if I make that scrollable, you'll see that there's a module called classifier, and the one change we can do is just replace this one layer with, I did two output features last class. I changed that to one because we don't want to account for the possibility where it could be simultaneously yes and no or neither. So switched that out, and this is something that one of us caught earlier. Something that is standard in natural images, but since we're dealing with brain scans, we take out the normalization for color channels since our data is grayscale. Then we load a sample from that, look at what its label is. So we have each element returned by the data set object is one sample and the label that goes with it, because that's how we wrote it. After that, to train the model, we also want the ability to evaluate it on unseen data. So we set aside some data. And last class, when I did it, I only split it into train and test. This time I'm doing three instead. So one that we'll be using during training, but not to update the weights, only to sort of guess how well it will generalize. And we wrap our data set, each split, with a data loader that lets us do batching and shuffling and use multiple threads to load samples. And then we do the actual training part. So the way to change the layer is just find the last layer and reassign it. Just supply your own layer that replaces it. This is a quick check to see if there is a GPU present. If your system has more than one GPU, then you'd have to do a bit more setup to be able to use both of them and sort of define how you want to split your training, whether you do like part of the model architecture on one GPU and another part, so we could put the feature extractor on one GPU and the classifier on the other one. That would be model parallelism. And then the other way to do it is if you have, say, 64 samples in one batch, then you can put 32 on one and 32 on the other. That is data parallel training. So we set all the parameters except for the last layer that we just applied, set everything except that non-trainable. We're freezing the weights and only making that last layer trainable. Then we define the loss function, which earlier for the two output neuron formulation, we were using cross entropy. This is binary cross entropy, which expects logit values coming out of just one neuron. And this has a sigmoid built into it. So we just give it raw values. Our model will not have a sigmoid or softmax active. Softmax doesn't even come into the picture here because it's just one neuron. but we don't do our activation at the end. And that's a PyTorch design choice rather than just the standard way of doing it. I'm not sure how it would be in TensorFlow or JAX or Keras or whatever. Oh, Keras V3 now lets you use whatever backend you want, so you can even use Keras with PyTorch. Pretty cool. I haven't tried it out yet, but it's worth looking into because the sort of syntax to define models and train them and stuff is a lot more abstracted and simpler. And you can progressively see more detail, but PyTorch, you just define everything directly. So it works exactly the way you tell it to, and there's no assumptions. Um, I also reorganized the training loop a little bit. So I now have functions that sort of wrap some of the training logic. So instead of having everything in one grotesque loop, I divvied it up a little bit. There's the train part for each epoch. There's also an evaluation function, which we'll be using for both the validation set and also the final test set. So the reason why we're doing validation along with training, I'll talk about that in a second. In case we didn't do transfer learning, then this is also something I did last class. We defined this model, and this is the one that I was able to get to work first, if you'll recall. Pretty much the same thing over here. Just wait, where'd it go? I thought I had a training output for that. I guess I took it out when I was cleaning stuff. Well, anyway, this is, yeah, okay. So I switched back to the MobileNet model, and then here, this is just training it for 10 epochs. Loss on the validation set is something that we're able to see. So this validation set doesn't get used to update the weights, but it only sort of gives us an idea of how the model is doing on unseen samples. And loss seems to be going down, but it's kind of hard to say what's going on. If we had graphs, that would make stuff a lot faster to interpret. So we define a little function to do that and then run our training again for 50 epochs this time. So reading this is a lot more involved, and we're not going to do that. But we have a graph that tells us that, oh, our training loss really spiked at one point. Validation loss also started climbing. So this isn't a really effective model. And we'll tweak it a little bit. So instead of just training the last layer, I set every parameter to trainable, lower the training rate, learning rate a little bit, and then do the same thing again. And now it seems to be doing a bit better. We're able to hit like 85 something percent validation accuracy. We still don't know how this is going to work on completely unseen data set. And the reason we set aside a test and in a test set in addition to a validation set is that there's something called early stopping, which we did last class. So that sort of, it doesn't directly influence the weights that you're learning, but since you're using the validation set to decide when to stop your training, that is leaking a little bit of information to the model because whatever performance is best on the validation set is what you use to decide when to stop training. So we want something completely unseen, which is why we hold on to a third split test set. And I just did a couple more changes, added another layer, added some nonlinearity with the leaky ReLU activation function, did a dropout for regularization, and tried to see if that helps things, and it didn't really make things better. So, because there's a lot of oscillations here, and it uh, seems to be converging until like 60, 70 epochs, and then after that, it diverges. So instead of that, I switched to the larger model and ran it for a whole bunch of epochs, about 100, and that got us up to about 95% validation accuracy, which seems pretty good. Uh, these, well, it was, I hadn't made it up to 95 when I was writing all of this stuff last night. Uh, yeah, so just a few sort of tweaks that you can make, and I'll upload this. Oh, another thing is learning rate scheduling is something that we can do. So it seems to be going down pretty smooth until this point, and then we see that it's sort of oscillating around optima, and we'd like to see it a bit smoother than that. And this is potentially because learning rate's too high, too low. So we mess around with that a little bit. There's three types of schedulers that I use. There's linear, cosine, and exponential, and I tried out all three of those. So exponential is over there. This one has the cosine annealing, and above that, I think, yeah, there's the linear scheduler, which I must have defined somewhere here. Yeah. So all of these modify the learning rate based on some logic that has to do with how many epochs into the training process you are. So just things to play with. And then, yeah, there's all of these things that we did, but at this point, we're not saving any models. So I added in early stopping logic, which is basically it will look at some metric that you just typically it's done based on a validation loss. That's like the right way to do it. I cheated a little bit and tried to use the validation accuracy instead of validation loss. And the logic is that if accuracy keeps decreasing for what is it, 10 epochs, which is what I set the patients to. So 10 consecutive epochs, if validation accuracy doesn't increase, then I just stop my training and save the weights from the best epoch. Actually, this right now is saving weights from best plus 10 epochs, so that I would have to change that. I'll change that before I upload this. I'm not dwelling on this too much right now because there's something cooler that I want to do now live. And it's probably going to take me a while. I don't know if I can finish it. Does anyone want to guess from the file name what it could be? A hint? It involves segmentation. It's something that we've all used, I'm assuming, at some point. Have we all done, we've done Zoom meetings and like FaceTime and stuff, right? Background blurring. Do you guys think that that's something you would want to see? Okay. All right, how much time do I have? It's 10:53 now. I have about 1 hour. I'll try to Uh, power through this. Okay, so let's build a game plan. First thing we need is to be able to read my webcam because that's what I'm gonna do. I want to do it real time. So read webcam real time. Then we gotta convert images to torch format. We also need a model that can do instance segmentation. Then we predict on webcam images, and where mask is false for class person, blur the image. Does this sequence make sense yet? You could, it's possible. I mean, what it depends on, the only thing you need a network here for is to get a good segmentation mask of where a person is. So if you have a way of doing that that doesn't involve neural networks, it will still work. Um, you could try to use something like hard cascades, which is built into OpenCV. We saw the Viola Jones detector, which was able to draw bounding boxes around like faces or your palm or whatever, but we need better than a bounding box because what we want is the outline. And we could try to apply some logic to that, like cluster within each bounding box, but uh, the objective of doing this is also to show how something like this is used as part of a pipeline that does other stuff also, apart from just training and predicting on models. Um, does that answer your question? Yeah. I don't think so. Like blurring entire images, sure, but being able to do the sort of, yeah, that, so the reason we didn't have that in like Teams or Zoom or whatever was that to be able to do that real time, it needs to be as few operations as possible. So um, on static images, you have more time to process it. If you take like 4 seconds, 10 seconds per image, that's still okay. Yeah, yeah, combinations of stuff like that. I'm not sure what the actual exact implementation would have been, but um, some combination of things that we've seen so far, I think we'd be able to build it with getting a bounding box around a person with Viola Jones and then some logic to sort of separate background from foreground. We could do like super pixel segmentation. There's things like grab cut. Um, what did we do? Canon, K means um, stuff like that. Okay, gotta lock in now. First thing is to add our if main, which is if name. Man, I hope my copilot doesn't give up on me. Oh wow, I did not need that much. Um, just the boilerplate. Nope. Then we run our main function. That's it. We'll define this in a second. Def main, I'll just leave that there for now. Pass. And let's also make an argument parser just in case. Good practice just to have that when you're doing command line stuff or interacting with something as a script. So I'll make a parser and add model. Oh yeah, mask RCNN is what I was going to use. Device, I'll just figure that out myself. Um, what else could we need? Yeah. So first thing, let's try to just visualize what the segmentation masks look like, and then we can do the blurring step after that. So I'll call this viz mode, and make that what string default mask, and if it's not mask, then we'll do blurring. So gotta parse those args and pass that in here and have that accepted. So model, let's call that model type is args.model. If mask RCNN, then yeah, we gotta create. So we're not gonna do that from Torch Hub. I'll just get it from the built-in Torch Vision models import. Actually, it's in detection, I believe. Yeah, mask RCNN. There's a V, yeah, V2, and then mask RCNN. We want the weights from that. So then we come in here and load that along with the weights. We're not going to say pre-trained equals true. Instead, we do it the recommended way, which is load up the weights and default. That should be good, I believe. And then there's also the transforms that this has. So that's one of the cool things they're doing now. I think it's a new way of doing it. They include the transforms that it expects as part of the weights. Weights transform. Okay. At least I think that's how it's done. We'll see in a second. Weights equals weights, and then move that to the device. So that gives us our model, which is loaded at this point, and we don't need to update it. Its weights. We're using pre-trained, so we set that to eval. Okay, yeah, that should handle the model loading part. So now next thing that we need to do is open up my webcam. So CV2 video capture, and the 0 is the sort of hardware address for image devices capable of capturing image frames. So we want to do that real time. So we define a while loop and cap.read, which returns two things, I believe. One of them is a flag that says whether it was successful or not. So if it was unsuccessful, then instead of breaking, we'll just skip to the next iteration, I guess, try again. And if not, then we have a frame. So remember that OpenCV loads it in BGR, so we convert that to RGB because everything else accepts RGB. And before doing all the tensor stuff, let's just check if we're able to see the frame. So I'll comment that out now because I'm going to be doing the display part with OpenCV. And this basically says if I press the button Q, that it will exit out of the loop. And I also want to release my camera once I get past that part, just for good cleanup, so it doesn't break anything. And then I'll close all windows and just return out of that function. And yeah, I guess that's pretty much it. So now The only thing we should be seeing when I run this is my webcam feed. And if that shows up, then we're good to go. Uh, transform. Yeah, that's probably it. Yeah, okay. Ooh, food out of, oh, yeah, of course. This thing's hogging all my VRAM, so restarted that. That should free up all my memory. Yeah, I have about 7 gigs free at the moment. Why does it take? Yeah, whatever. Okay, back to this. Let's try running that again. Should run this time, I guess. Um, okay, yeah, so webcam is up. My feed is up. It's real time. Everything's good. I press Q, exit out of that. Now we can start trying to pass all of this into our model. So we have our model loaded up here. Now let's predict on a, yeah, predict on image. That's good. Model, image. I'm gonna do, I don't like that. Okay, so Torch Vision transforms. I'm going to use the newer API from Torch Vision that transforms v2 import functional is what I want because I want to do everything inline. I'm not going to build a pipeline, just a choice. There's no reason for that really. Okay, so it needs to go in the model. First thing we got to do is we get the frame. Let's see where that would go. It should go about here. So we converted that to, um, actually, let's CV to torch image and do that in here because that's just cleaner. There's a few transforms they give us, which are pretty handy. So it converts it to a PIL image after we give it an RGB image. The only change there really is the object type. So it still has all the same values within the array. And then we convert that to a tensor. And since this is like a natural kind of image, I'm going to do the normalization step. Actually, I don't think I need to do that. Well, let's see if I can get away with just applying transform directly by passing that in because we do have that here. Okay, what I'll do is for each frame, once I converted it, I'll say CV to torch and pass transforms in there. And let's also see what transforms it's applying. So I'm gonna leave that in there. For now, I'll just pass that. So that function doesn't do anything at the moment, but Python shouldn't complain about that. And now if you're using your own model with pre-trained weights, then odds are your weights are not in this format and you'd have to define your transforms like that. So I'll leave them commented out in there. But let's see if we can apply that because that should make our life easier. And let's also just print out what transforms are applied. And that will return the image. Let's also just quickly check the image dimensions and data type. Image D type is image.d type. Okay, so we call that in here, and we're not doing anything with it. We're still displaying the same frame. Let's run that and see what it does. Oh, this is probably going to be really noisy because it's within what happened with our object detection. This is 438, line 28. It takes one positional argument, but two were given object detection in it. Let's see what it expects. Oh, wait, and I guess there's something I'm missing over here. Nope, that's not it. Lights are over here. We can just go in here and look at what it wants. So this is a class which is an enumerator versus init method. Wait, enum verify get state. Don't. I don't think I'm doing the right thing. Okay. Well, let's just DIY it, I guess. Unless I did ask it to print out what the transforms were. No, it didn't get that far. So yeah, this is newer, so I haven't done that method a whole bunch. I, oh, is it failing before we get there? Image? Nope. Okay, that is where it failed. So let's undo that or leave that in. Uncomment this stuff because that should be what it expects, I'm pretty sure. And we'll still print out the transforms just to see what's going on. Maybe I'll move that out of there and down here where we first get that. And let's run this again and see. Okay, so that was not very helpful. But yeah, BGR. Okay, so this is a float 32 image. Channels are first height width. Ideally, this would be unsigned integers because it should it would expect, what do you call it? Pixel values in the range of 0 and 255. So we're gonna convert this to, okay, image to tensor. I think, yeah, we should probably normalize it first, and then I'm honestly not sure if that'll work, but we'll find out. E-type, charge 2.8. So with a maximum range of 255, guess we should also just check what pixel values are. Image.min and max, just so we know what we're dealing with and what my camera is returning. Image value range. Okay. And that should also tell us whether our conversion. Okay, so by this point, it expected a tensor to do the normalizing. So I'll do that step after. So uint8, and let's also check that after typecasting. Oh, it's an image object still at this point. Okay, if it is a PIL image, then I think we should be fine converting it. P-type is unexpected. Oh, F.2 tensor. cursor. Did I import torch? Yes, I did. Okay. I think I can. Int, but I want unsigned int, so maybe I can do this. Tensor. B type is Hue and Tate. See if that works. Oh, it wants a float. Oh, that's my bad. Right, yeah, that totally makes sense. Float 32, we have our labels. Min max of 1 each. Okay, that's odd. Maybe I should rescale these. We'll see. Okay, let's plug it into the model now. So we have our image at this point, and we have the model. So in here, at this point, this is a what? Oh, we also need to supply device because we model is already on the device that we want it to be. Here, since we unsqueeze 0 to add a batch dimension at the start, because that's probably what it expects. If not, then we can take that. Actually, let's not do that just yet. We'll see if the model complains and then decide whether to do that or not. So we move the image. We can just do that over here to device. So this is more concise, and that returns a prediction, and we can print that out here once we call it. Okay, so I think at this point, this all of, wait, we don't need transforms there. What's that? Okay, so we're not using our transforms in there, we're just doing it ourselves. Predict on image, model image device. We supply our model here. This is so that we're not computing gradients, since all we care about is just making a prediction. We don't want to make weight updates. We also set it to eval over here, which does something similar. Weights transforms. Okay. Main, we're going in here, supplying, yeah, that should not be there. And CV to torch image gives us the image, model, image device, and make a prediction. And let's run this and see what happens. And I'll also take out my prints because this is really noisy. Actually, I'll leave that in there for now. And aha, list of 3D tensors of shape, channel height, width, cut, torch size, 480, 60. Okay, so what happened here? The final shape, before it goes into the model, we need to check that just to see what's going on. So print image shape. This is before prediction, so I'm going to take out all of this other stuff just so we know where everything's coming from. And we should see one of those prints. So it does have the channel over here, which means that it's expecting batched input. So we should be doing the unsqueeze, and we'll do that over here. And that will add one more dimension right at the start. So batch size, channel height, width, and that should show up as print statements also when we run this. And okay, yeah, so it's running predictions, but we don't know what it's predicting really. There's this whole bunch of stuff. We see that there's something that looks like a dictionary with the word with the key masks in it, and that has a tensor. There's also labels, scores. Now, normally this would be documented and everything, but and it is. I just want to sort of walk through my process of digging through all of this when you don't have that information. So I'm just going to pretend we don't have documentation for this. We predicted it, so we know that it. Let's see what the sort of top level prediction looks like. If we can tell, okay. So it's a list with a dictionary in it. I guess first thing, so the list should have however many samples we have in our batch, because one prediction per sample. And that means that, let's see, length should be 1. That's my guess. And operating under that assumption, I'm also going to print out what keys each prediction dictionary has, just to see if there's anything apart from boxes and masks. And I'll just rerun that. And how are we doing on time? 11:20. Oh, that is not good. Okay, I'll speed things up a little bit. Okay, so we see there's boxes, labels, scores, masks, and now let's draw our segmentation mask. So we can do that using from torchvision.utils, import, draw bounding boxes, draw segmentation masks. Okay. So now, predict, yeah, we should do that in here. Now, okay. Masks are in prediction masks. We know that because we know it's a dictionary. Boxes are in prediction boxes. Labels are in prediction labels, and scores are in scores. Now we look for okay, this part I don't want to figure that out myself. So what I'm going to do instead is start vision mask just the way we're able to do that. Where's the weights? Models and pre-trained weights, instant segmentation. And I think if I click on that, then there's an example of using the new API, using pre-trained models, resonate. So this is for classification from hub. NASCAR standard. Oh yeah, there we go. Visualization for instant segmentation. There's the weights transform. So this part is what I was trying to do earlier. And masks, dog masks. Shape, okay. Yeah, that's what we want. Um, and hang on. This was a simpler example, I think. Grid, drop animals. Okay, whatever. We'll figure it out. So image with mask, draw segmentation masks, and we can see what it expects. The image, mask, alpha, colors. So we pass it the image because we have that. We pass it our masks. And alpha is the transparency for the mask, and I'll give it the color. Um, I wonder if I can pass a color map here, but this color can be represented as PIL strings. Okay, so I'll just call it green. And then turn prediction and image with mask. Let's return that also. We're not doing anything with the boxes, labels, and scores just yet. Let's first look at, actually we don't need the raw prediction really. Image with mask, and then we can, oh, we also need to convert this back to whatever OpenCV format. So before doing that, let's call this, don't need the length over there, but we do need to check its shape really quick. And it will have extra dimensions, which we'll have to squeeze, but just we'll get to that in a second. So I'm sure we're showing frame over here. Instead of that, we call this masked image. And we first convert that back to RGB. No, BGR. CV2 color, that's uppercase. Color RGB to BGR. What is it not like here? Oh, I'm sure. Okay, what am I missing? Oh, I didn't close that. There we go. Okay. Pass individual images, not batches. Hmm. Hmm. Where did this happen? Thought we were getting predictions. Oh, this is when we're okay. Let's look at our mask shape, and I'll also squeeze our masks just to get rid of any extra. Okay, shape squeezed. So yeah, we had to be squeezing just the initial one, not the second position or whatever. So I'll just get rid of that one from in there, and that should fix it, I believe. Oh, shape game. There's 19 masks. Okay. So I guess it found 19 labels. Um, let's look at the labels really quick. Print labels, and Okay. Uh, they're all 10, 10, 10, 44. We need to resolve that into what the what they mean. So let's also pass um, weight in here, um, which is this, and then should be able to. Oh, I didn't update the definition. Weights. Um, then we take weights, labels. So this should be a dictionary, I think. Weight, labels, and predicted labels is. So this is still going to fail, but I want to see, what is it? The tensor is deprecated, CVIP. No attribute labels. Okay, let's see what it actually has. Transforms, meta, URL, NASCAR CNN. Um, let's see. How do we get labels? Um, instance, output that. There's some masks. We want to see mask names, weights that meta categories label. Okay. So going back to our thing over here, this should be weights that meta categories, and that just prints out all the categories, and we do the exact same thing over here, label for label in labels, and do that for all of them. So that should tell us what happened. That closes it. Categories, labels, label for, label in, labels. What's wrong with that? Versus failing. Unmatched. 42. Oh, yeah, of course. That's not going to work because it's double quotes within double quotes. So I got to change that to that, and we should be good now. Okay, so that's all the labels that we have in here. And predicted, oh wow, it thinks I'm traffic lights and a bottle. Weird, but we can work around that. Okay, next thing we need is okay, you know what? I'll just flatten everything that I have into one mask and just plot the whole thing. Because let's see, masks fused is torched up. Actually, yeah, I think that would still do the same thing along mask shape. So there's 20 masks that are predicted, and we want to flatten that into one. So dimension 0 is right, and then we unsqueeze that. Now we squeeze it. We'll squeeze the whole thing, and then let's see what that does. So now this is 289, line 50, cross segmentation mask fused is past individual images. Let me squeeze that also. Thought I did that. Guess I did not. Okay. Height width. Mask must be shape of height width or batch size height width. What's our mask shape at the moment? Oh, it's still 15. Mask fused. Oh, right. Yeah, because we're passing the wrong thing in there. Now, God, it should be of type bool, which makes sense. So I'll just typecast that really quick. Module object is not callable. Okay. Guess I gotta torch dot. How did I do it earlier? Tensor and d type equals torch dot bool. Okay. Guess that should do it. Where else did I do the tensor stuff? D type. Oh, okay. It's the only place. It's never closed. That was my bad. Mask is not callable. Masked image. Image with mask is what it's returning. Predict is masked image. CV2 dot CVT color. Okay. So at this point, it expected a NumPy array, and this is still a tensor. So the image that we return over here needs to be moved back to the CPU, converted to NumPy. And we also want to detach. So model image to device, and then let's do prediction dot detach, just so it doesn't keep hogging all my memory and whatnot. Detach dot CPU. I'll move it right here. Actually, I'm not going to do that. Yeah, that should be good. Image CPU numpy. So at this point, what it gets over here, this should be a numpy array at this point, and we should be able to show that list object. So okay, forget about detaching it for now. Just try to run it. It's doing something, but it's not very good. Masked image shape. Oh, this is still the wrong dimensions because we need it to be Vermeer. we need channels last to be able to visualize it. So I'm just moving the axes around. And this has to be before I convert it to NumPy. So I call that first and then convert to NumPy. Okay, so there's masks everywhere, seems like. Um, Maybe if I flip it around a little bit, get rid of the light. Uh, okay. You, you guys can see the like masks around stuff, right? It's just that there's a everything's really bright, so um, but it is detecting me, and I think it also might be printing out person somewhere in between. At least I hope it is. Uh, Mask shape. I should get rid of that one print that's printing out all the labels that it recognizes and clean that up a little bit. But so far, so good. The only thing left to do is blur everything that's not a person. Um, okay, transforms, masked image shape. We don't need, I'm just going to get rid of all our prints. Um, oh, I think I broke something. Yeah. Uh, yeah, we still want that. Okay. Predictive labels is category. All right. Let's see. Let's see what that gives us. Oh, it thinks I'm a traffic light. That's unfortunate. Percent. Um, okay, I'll quit out of this and let's see if we can filter based on label really quick instead of doing the sum or in addition to doing the sum, not for. Uh, um, let's see, labels. Let's hold on to that and call this oh, label names, um, predicted label names. No, just leave it like that. And for mm, okay, and so prediction 0 has our current prediction is in prediction 0, just so that it's a bit easier to parse what's going on. I'm renaming stuff. And we call it current prediction. Um, these are all the current masks that we have. We don't care about boxes for now. We don't really care about, oh, I should also probably filter by scores. Yeah, so for pred and current prediction, um, we keep, let's call this filtered is pred for pred in current prediction if pred what is it? Score. Oh, that doesn't work. We also need to hold on to the index, so I shouldn't be doing this as a one-liner. Let's see. Mask is that, labels that, scores that, and boxes that. Um, prediction. Wait a minute. Does that work? If that if scores is less than 5, then we don't care about it. Filtered predictions is an empty list. Else we append it and then set our current predictions to that. Then we do another one, filtered by class. And then label 0. Okay, so here label names is that, and then if person in label names, yeah, okay, filter class, and then you take that and our masks. Okay, this is gross, I know. There should be a better way to do it, but right now that's the best I can think of. String indices must be integers spread. Where did this happen? For 947. For string indices. Okay, so this is already a string at this point. Current prediction is prediction 0. Okay, that's what I get for trying to do too much at once. Current prediction, where did that happen? For in current prediction. So at this point, it's prediction 0. I'm just going to comment all of this out. And actually, I did too much. I got a little confused. Gonna undo some stuff. Predict labels. And I guess rather than trying to filter by score, I'll just do it based on class. So filtered by class. Label index for person is, oh, that's neat, nifty. Labels. This gives us a mask, and then that filters our masks and scores. Yeah, that is definitely a better way to do it. Then we fuse all of them, squeeze them, and yeah, hopefully that works. Let's see. Predicting labels first. Okay, so this we're printing a bit early. Let's move this down. Oh, whoops. Masks fused, filtered. Print. Labels after